Hello. Question 9 on the midterm gives us a matrix A and the reduced row echelon form of the coefficient part, at least, of an arbitrary augmentation of that matrix. By arbitrary, I mean that the vector on the right is just an arbitrary vector. And then it asks us several things about this system. So the first question that we're asked is pretty easy. What is the rank of A? So the rank of A we can see from the reduced row echelon form here is just equal to 3 because we have these 3 leading entries. So here we are, 3. Now the second thing they asked is this particular vector here in the column space of A? So if it was in the column space, how would we check that? Well, we would write this augmentation here, where A is 1, B is 1, C is 1, and D is 0. And then we would row reduce to check to see if we get any pivot positions over here on this row reduce version of the augmentation. Now, the only way that we can get a pivot position in this part over here is if this bottom formula down here is non-zero, because then we would get a leading entry here. Otherwise, it doesn't matter what these 3 values are because we have a leading entry there, there, and there, so it's not going to force this to be a pivot position. So the question is really just asking, is A plus B minus 2D equal to 0 or not? But we can see that A plus B minus 2D, in our case, is equal to 1 plus 1 minus 2 times 0, which is 2, which does not equal 0. So we get that it is not in the column space of A. So our answer here is no. And we can say since the rightmost column in reduced row echelon form is a pivot column. Since rightmost column is pivot column, is a pivot column, pivot column. All right. The next question that we're asked is to find a basis for the column space of A. All right, so we know how to do this. All we have to do is take A, put it in row echelon form, identify the pivot columns of the original matrix A, and then write those down. So I'm going to go ahead and do that here. Maybe over here is the best way to do it. So I'm going to write, beta is equal to, we've been doing sets for bases, so we're going to go ahead and use that. Our first pivot column over here is going to give us this guy as our first basis element, 0, 0, 1, 0. Our second pivot column, which is the third column, is going to give us this third column, 0, 1, 1. And I'm almost out of space. I think I can do this. And our third pivot column, which is actually going to be the fifth column of the matrix, is what we get, 1, 1, 0, 1. We can do it. There we go. Okay, so this is a basis for the column space of A, because they are the pivot columns of the original matrix A. So now what I want to do is, okay, I rewrote the question a little bit because I didn't want to write this guy vertically. But we want to write this vector here, which is actually a column vector, I did this clever trick, as a linear combination of the basis found in 3. Okay, so if we wanted to write it as a linear combination of these vectors inside of the column vectors of this matrix here, then what we would do is we would put it on the right-hand side, and we would row reduce, and we would try and then figure out what the solutions to that system were. Now, if we could then write it out so that that linear combination didn't involve any of these extraneous vectors, then we would have it as a linear combination of the basis found in the original guy. So how do we do that? Well, all we need to do then, if we want to do the reduced row echelon form of this mother this big matrix here, then we just have to plug in these values for A, B, C, and D into this guy, and then solve for the solutions. And what we'll really have to do then is just set the parameters equal to 0, and that'll give us what we want. So over here, we can go ahead and write it out. So I'm just going to write out the rightmost part here. Okay, so we're going to get minus A plus C plus D. Okay. In our case, that's going to equal, this is minus 3 minus 2 plus 4. So it's going to be a minus 1. And now the second equation, A minus D, okay, this is 3 minus 4. That's minus 1 as well. And then our last one, or our third one, is going to be minus A plus 2D. That's going to equal minus 3 plus 8, 5. And then this guy down here is going to be A plus B minus 2D. All right, what's that going to give us? That's going to give us 8 minus 2D, which is also 8. So we get a 0 here. Great, that's good. That 0 down here, this last one being 0, it means that it is a linear combination of these vectors. That's good to know, because it means that this guy's not a pivot column. So now let's go ahead and figure out what all the solutions would be. Okay, all the solutions, we would have, we would set our free variables equal to parameters. We've got a lot of free variables, and then we would write the other variables in terms of those parameters. But now, if all of our parameters are 0, then what do we get? We just get that our x1, this basic variable, our x3, which is our other basic variable, and our x5, which is our, x6. Ooh, yep, yeah, x6, oops. Our x6, which is our other basic variable. Okay, well, this guy is just going to equal minus 1, this guy is just going to equal minus 1, and this guy is just going to equal 5. So this means that the corresponding linear combination that we get from the solution is just going to be minus 1 times our first basis vector. This minus 1 for x3 is going to give us a minus 1 times our second basis vector. And then this 5 is going to give us the coefficient in front of our third basis vector. And hopefully, this is going to be 3, 5, minus 2, and 4. We can go ahead and double check that real quick, since it only takes a second to do this computation. Here we have minus 1 plus 5 is 3. Here we have 5, 0, and 0. Minus 1 gives us minus 2, and then minus 1 plus 5 is 4. So it worked out. Okay? All we're doing is using this guy here and then getting rid of the redundant vectors that turn out to correspond to our free variables.